Shall we begin now?
Yes, sir, we are right.
Yeah. Hello, students. Welcome to a live session with time on this subject chemistry and this chapter solutions. We are going to continue. This is the third part of this chapter solutions. Now, in the previous sessions, which you'll be finding in the YouTube, so you can check the YouTube channel so that you can get interesting videos on all the chapters pertaining to 12th and 11th for engineering as well as medicine entrances and any other entrance exam that you'll find. Now, in this session, we are going to take up the third part, which we had started as colligative properties. Now, there are 4 colligative properties, but just before that, let me tell you that we had already done 2 sessions. One session on Henry's law, where gases are dissolved in liquids, and we had done also the Raoult's law, where both the liquids are volatile or both the components are volatile. And this is the third one where only one component is volatile. That is, the solvent is a volatile one component and the solute is non-volatile. And herein we observe certain special properties called colligative properties. In the previous session, we had mentioned that colligative properties are properties which depend on a collection. Collection means what? Collection means it could be the collection that we usually employ in chemistry, and that is the Avogadro's number, which is also called the mole. So we deal with moles. So the collection is the mole. This mole could be part of a solvent whose weight is in kg, then this will be called the molality. Or the same mole may be part of the solution whose volume is given in liters. So then it will become the molarity. So molality or molarity are dealing with this moles. So if the moles you have per kg of solvent, it is called molality. If you have the same moles in 1 liter of solution, then it is called molarity. So colligative properties depend on the molality or molarity or the collection of the solute particles in a given solution. Now, what are all the colligative properties that we have? We have a lowering of vapor pressure when a non-volatile solute is added to a solvent, an elevation in boiling point, a depression in freezing point, or osmotic pressure. So these are the 4 colligative properties which you'll be interested in, which are all dependent on the number of particles, number of solute particles. When you take lowering of vapor pressure, elevation of boiling point, and depression of freezing point, you'll find that the equation employs molality. Whereas when it comes to osmotic pressure, it is molarity. That's small change. So lowering of vapor pressure, elevation of boiling point, depression in the freezing point, they're all dependent on the molality of the solution, which is number of moles of solute per kg of solvent. And osmotic pressure is number of moles of solute in 1 liter of the solution. Clear? So we'll take up each one. Lowering of vapor pressure, elevation in the boiling point. So there is a decrease in the vapor pressure. There is an increase in the boiling point. There is a decrease in the freezing point. And there is osmotic pressure, no decrease, no increase, absolute value. So for the first 3, we have delta. Delta means difference. What was there when only solvent was there? What happened when the non-volatile solute has been added to form a solution. So when a solvent is turning into a solution, right, with the addition of a non-volatile solute, what is happening to vapor pressure? What is happening to the boiling point? What is happening to the freezing point? So there is a decrease in vapor pressure, there is an increase in boiling point, there is a decrease in freezing point. Clear? Whereas the fourth one is an absolute value. We'll start with the first one, right? I hope you have taken up all these things, right? We'll now look at if anybody has got any questions to ask, right? Otherwise, we'll continue with the lowering of vapor pressure. So here I would show you what happens when the vapor pressure is being lowered, right, from P0 to P. So here I have shown you this only because I thought I'll get the space there for time. So P0 minus P by P0 is equal to XB. That is the mole fraction of the solute, right? So here we find that there is a lowering of vapor pressure. I'll put it here. P0 is the vapor pressure of the solvent, and this P0 came down to P. So there is a lowering of vapor pressure. So P0 minus P is delta P, which is a lowering of vapor pressure. That delta P is proportional to M. There is a molality. Clear? And how this is, that we'll show here. Now P0 minus P by P0 equals XB. XB is nothing but the number of moles of solute by total number of moles, because that is nothing but the mole fraction of the solute. And because it is a dilute solution, in a dilute solution, what happens? The number of moles of solute is much less when compared to number of moles of solvent. So in that case, we can replace or we can remove this NB, means we can ignore this NB in the denominator. It's something like a drop added to an ocean. So we can remove this drop. So that is NB by Na. So NB by Na. So what is NB? Weight of the solute by molecular weight of the solute. What is Na? Weight of the solvent by molecular weight of the solvent. Right. What I'll do is I'll multiply with 1000 and divide with 1000 so that whatever I have circled here, this part is the molality. What is the remaining thing here? There is an Ma and there is a 1000 at the bottom. So M into Ma by 1000. So if I take this P0 minus P, which is delta P, I can send the P0 to the other side. That will be P0 into Ma by 1000 into M. This part is nothing but a constant value for a solvent. So delta P is proportional to M. That is what we get. Clear? So delta P is proportional to the molality. That is what we get. So this is what is a summary of what all things we did here. So this is coming from the Raoult's law. From the Raoult's law, we have applied the Raoult's law for a situation where there is a solvent to which there is a non-volatile solute added up. So that way we'll have the entire solution's vapor pressure falling, and that falling depends on the molality here. So if I may show, P0 minus P by P0, right? This is equal to XP. This is Raoult's law for a non-volatile solute here. So this particular equation is of great importance because when we solve the problems, as you will see now, you will get to know how important this equation is. Moving back, we'll take up now what happens to the vapor pressure. This is the solvent, and you have added what? In non-volatile solute. When you add a non-volatile solute, the P0 is brought down to P. Are you able to see the number of solvent molecules, right, on top in the vapor phase? And how is the number coming down when you had added a non-volatile solute? This is a non-volatile solute. The orange one is a non-volatile solute. The moment you add a non-volatile solute, the surface is also occupied by non-volatile solute molecules, and the tendency to undergo evaporation becomes less because evaporation happens from the surface. So when the surface is having less of the solvent, right, there will be less of evaporation because solute doesn't evaporate because it is non-volatile. Non-volatile means not giving vapor. So there is a lowering of vapor pressure from P0 to P as you add a non-volatile solute. That non-volatile solute, we are giving a symbol B. For a solvent, we use the symbol A. I hope this is clear. So P0 coming down to P upon addition of a non-volatile solute. More non-volatile solute to add, more will be the lowering of vapor pressure. The delta P is proportional to M. I hope this is clear. We'll now move on to the elevation in the boiling point. Just before we come to this, I would like to show on an empty slide so that it is clearer. Now, what is boiling point? Boiling point is the temperature at which the vapor pressure of the liquid becomes equal to 1 atmosphere. Here. Now, let us put that 1 atmosphere here, and let us put the liquid here, liquid A, right? This is 1 atmosphere, and this is the vapor pressure of A. Now, what happens to the vapor pressure as A is coming down to the swarm of a solution? By adding a non-volatile solute, there is a lowering of vapor pressure. So shall I take this as A plus B? This is the solution, right? Now, for A to turn into vapor, that is into the gas directly, you need to heat. And for the solution, also we need to heat, because heating is required to convert the liquid, whether it is the form of a solution or in the form of a solvent, to vapor. That is vapor pressure of the liquid becoming 1 atmosphere. The temperature at which this happens is the boiling point. So where do you require more heating? For A or for A plus B? A is already closer to 1 atmosphere. There has been a lowering of vapor pressure. This is delta P, right? Because of this delta P, A plus B is down in vapor pressure, and therefore we need to heat more. So more heating is required for the solution, less heating is required for a solvent, and therefore there is an elevation in the boiling point. So boiling point increases, right, as we move from A to A plus B. So as the vapor pressure lowers, there is an elevation in the boiling point. I hope this is clear. So as the vapor pressure falls, there is an increase in the boiling point. So the solution will have greater boiling point than the solvent. So solvent's boiling point, will put it as TB0, and solution is TB. So TB is more than TB0. So on this line, if you're looking at this as TB0, then this is TB. So as the vapor pressure falls, there is an elevation in the boiling point. I hope this is clear. So why is the solution requiring more heat? It is because its vapor pressure is lower. There has been a lowering of the vapor pressure, and therefore you require more heating. Therefore, the boiling point is more. So these things are all summarized here. For want of time, I thought I'll put this like this, because every time we do an explanation, there are so many things that we need to write and then put it here. So for want of time, we have put this so that it will be handy. So delta TB is also proportional to the molality, because it is proportional to delta P. So that is how delta TB is equal to Kb into M. So what is this Kb? This Kb is the value of Kb is equal to delta TB when M is equal to 1. Therefore, this is called molal elevation constant. That is, if you have a 1 molal solution, that 1 molal solution will have a Kb value equal to the elevation. This is the elevation, right? Elevation or the boiling point. So sometimes you may also call it molal boiling point constant. It is a constant value. So it is a constant. For 1 molal solution, what is the elevation? That is a Kb. So it is also called ebullioscopic constant. Molal ebullioscopic constant, because ebullioscopy means boiling of liquids. So molal elevation constant or molal boiling point constant or molal ebullioscopic constant is this Kb. That Kb is dependent only on the solvent. Kb depends only on solvent, and this is how it is related to the boiling point of the solvent, which is given as Tb naught. So Kb is R into Tb naught square divided by 1000 into delta H vaporization, enthalpy of vaporization, and the whole thing is multiplied with the molar mass of the solvent here. So you could also write the entire thing like this. I'll put it here. Kb equals R Tb naught square of the boiling point by 1000 into latent heat of vaporization. That latent heat of vaporization is in, let us say, energy units per gram. We have delta H vaporization as energy units per mole, right? So how to convert this L vaporization into delta H vaporization? You know that if L vaporization, right, which is in joule per gram, right, is multiplied, or let us say that you have started with this, how to convert, what is the molar mass? Molar mass is in gram per mole, right? So if I have joule per gram for latent heat of vaporization, the same thing I'll write as delta H vaporization by the molar mass of the solvent. So what is this? This is joule per mole. This is gram per mole. So this becomes joule per gram. Clear? So latent heat of vaporization is in joule per gram. So if you have delta H vaporization to be input into this, instead of latent heat of vaporization, I'll simply write R Tb naught square by 1000 into delta H vaporization into Ma. That is a molar mass of the solvent. This is what we have shown in the slide just before this. So this is the elaboration of the conversion of how to convert L vaporization into delta H vaporization, because delta H vaporization will be in what units? Joule per mole, whereas L vaporization is in joule per gram. So that this is nothing but the L of vaporization. I hope this is clear. Yes, we'll move on to the previous slide. Yeah, that is what we found here. So this is the Kb that we found here. So all those things are put on the left hand side here. So this is about the elevation in the boiling point. We shall now see the vapor pressure curves, right? Now this is vapor pressure versus temperature. For few liquids we have shown here. The first one is diethyl ether. The second one is ethyl alcohol. The third one is water. Water boils at 100 degrees. Ethanol boils at 78.4 and diethyl ether at 34.6. Here. So this is what is the curve that we have. Vapor pressure versus the temperature. So as the temperature increases, vapor pressure increases, but not linearly. All these plots are not linear. They are not linear plots. Here. So this is vapor pressure versus temperature. So if this is 1 atmosphere, then whatever is the vapor pressure curve of the solvent, this is A plus B. there is a lowering of vapor pressure. Therefore, there is an elevation in the boiling point. What is TB naught? TB naught is the temperature at which the vapor pressure of A becomes equal to 1 atmosphere. So from there, I have dropped the perpendicular here. That is TB naught. And where this 1 atmosphere is touching the A plus B curve here, from there I have dropped the perpendicular. So that is a TB. So the boiling point of solution here, this is the boiling point of the solvent. So there is an elevation in the boiling point as there is a decrease in the vapor pressure. Hope this is clear. Now the third one is the depression in freezing point, which we shall show here. Now delta TF is also proportional to delta P, which is proportional to M, and therefore delta TF is equal to KF into M. Now this KF is also on a very similar thing that we did for elevation of boiling point. So here if M is equal to 1, then KF will be numerically equal to delta TF. So it is molal depression constant. Molal depression constant or molal freezing point constant, or another word, molal cryoscopic constant, because cryoscopy is low temperatures. So high temperatures is ebullioscopic, where the liquids boil, and cryoscopy is low temperatures where liquids freeze. So freezing point constant or depression constant or cryoscopic constant, all 1 molal, because when you put M is equal to 1, KF is numerically equal to delta TF. That is the depression in the temperature or the freezing point or the cryoscopic. So that is how we have delta TF also proportional to M, and KF is very, very similar to what we wrote for KB. This is R TF naught square by 1000 latent heat of fusion or freezing. Both are same. When solid turns into liquid, it is called fusion. When liquid turns into solid, it is called freezing. And both will happen at the same temperature. It's an equilibrium, right? So here, the forward process is fusion. The reverse process is freezing, right? So freezing point or the fusion point is the same, or latent heat of fusion or latent heat of freezing is the same. And in a similar way that we showed for the previous one, we will have 1000 delta H fusion multiplied by MA. Very, very similar. KF is also dependent on solvent, right? KF is also a solvent parameter. It depends on the solvent. What? Molar mass of the solvent, the latent heat of freezing of the solvent, the freezing point of the solvent. R is anyhow the universal gas constant. Hope this is clear. Let me check if anybody has got any questions. Otherwise, we'll move on. Now, all these things have been summarized here, right? For the freezing point, this is liquid and this is a solid. So when the vapor pressure versus temperature is plotted, the same thing that you did for boiling. Boiling is at a higher temperature. At a higher temperature, the liquid will turn into vapor. But then here, the liquid is turning into solid. This is because this is going to be freezing. So what comes out? The solvent comes out. The solvent becomes a solid or crystallizes, becomes a solid, you can say, right? So it is a solvent that comes out of the solution as a solid. Suppose it is water. What comes out of water? Ice. Ice comes out. So solvent is the one that undergoes the solidification, not the solute, because solute is mostly a solid. Most of the solutes are solids because they have to be non-volatile. Non-volatile you cannot expect from a liquid, right? As much as you expect from a solid, is it not? So for freezing point also you have a similar formula here. And this is the freezing point of the solvent. This is the freezing point of the solution. So there is a depression in the freezing point. Now this is a more elaborate, more correct plots, right? This is from the phase diagram, right? Which is of course out of syllabus for us. So solid, liquid and gas we have. So freezing point of water to freezing point of solution, decrease. Boiling point of water to boiling point of solution, increase. And there is a lowering of vapor pressure. All the three are put into a single plot, right? Hope this is clear. We'll move on to the fourth one, osmotic pressure. Osmotic pressure is something like the pressure of a gas. What happens in osmosis is we have, let us say, a semi-permeable membrane. A semi-permeable membrane allows only the solvent to pass through. Suppose this is concentration C1 and this is concentration C2. And let us say that C1 is more than C2. So C1 is more means what? The solute is more. But what moves is a solvent. So this is a semi-permeable membrane. The solvent will pass like this. As the solvent passes, there is a decrease in the height of the more solvent side. And there is an increase in the height of the less solvent side. So as the solvent moves, there is a decrease in the height. So ultimately what will happen after some time is the levels won't be the same. Semi-permeable membrane, this has come down and that has increased there. And let us say that this gap is H, right? This is C2, this is C1, right? Now the osmotic pressure is the pressure that was from the solvent to the solution or from more solvent to the less solvent side. So that is a push that you have. But what moves is only the solvent. So osmotic pressure depends upon the C1 here. Because if you have more C1, there will be more rush of solvent. So the osmotic pressure is because of the driving force here, right? You find that when C1 is more, there is greater force of solvent to move from C2 to C1 side. So more the particles here, more will be the osmotic pressure. So osmotic pressure pi is proportional to, here you use molarity. So that is what we wrote here. Pi is equal to the molarity into R into T, which is very, very similar to PV is equal to nRT, the ideal gas equation, where P equals N by V RT. What is N by V? Number of moles by volume, volume in liters. So that is nothing but the molarity, right, into R into T. So pi depends on the molarity and the temperature, right? More the temperature, more will be the osmotic pressure. So all these illustrations would be found here. So here, this is a solution. This is the pure solvent. So check the arrow. The arrow is from the solvent to the solution, right? And then because of this, what is happening? The level has fallen down here as a solvent moves, and the level here goes up. Look at this. I put an equation here. H1 minus H2 rho into G. You know that HdG, right? It has a meaning. It has the unit of pressure. Yes. Now, as osmosis happened here in this side, it is from left to right. There is the level of water going up. So there is a hydrostatic head of pressure created. So as the osmosis happens, the height increases here. As the height increases, this will start putting pressure on the osmotic pressure, and then ultimately this will stop. The process of osmosis stops when the pressures on both sides are equal, right? How has this happened? This is because the water level has increased here and the hydrostatic head of pressure starts increasing and then becomes almost equal to the osmotic pressure. When it becomes exactly equal to the osmotic pressure, the process stops, right? So in the experiment, right, you perform the measurement of osmotic pressure through this. What we can do is we can put pressure on this side, right, and check when is the osmosis stopping. So the negative pressure that you put on the other side to prevent osmosis is also osmosis. correct? So suppose this is H1 and this is H2. That is what I have shown here, the height difference into the density, into the acceleration due to gravity, right? That is the osmotic pressure. In the next slide, this is even more clear. This is the back pressure. There is a hydrostatic head of pressure. The height differences come out. This is taken as H. So H into the rho, that is the density into the acceleration due to gravity. Clear? So osmotic pressure can also be measured as the pressure to be applied on the more concentrated side to stop osmosis. Clear? Now, isotonic solutions are what? Those where the outside concentration and the inside concentration is the same. See, inside there is 20% solute, outside also there is 20% solute. So there is no osmosis, right? Isotonic solutions are solutions where the number of particles are same. When number of particles are same, the osmotic pressures will be same. So there is no osmosis. But what is a hypertonic solution? There is more concentration. So here, look at this. This is 40% solute and that is 20% solute. 20% solute inside. So there is more water. So water will flow out. Water moves out of the cell, right? Because this solution is what? Hypertonic. More concentration of the solute. So water comes out. So there is a shrinkage happening. Clear? Next, here what is happening? The solute is less outside. The solute is more inside. So water goes into the cell. The cell is having more concentration. So the cell will swell. Clear? So here no osmosis, the first one. Second one, water flows out, leading to a shrinkage of the cell size. And then when water moves in, right, from a hypotonic solution, the cell swells up. I hope this is clear. Now, these are all the formulas that we have, right? So for the sake of giving you a feel of the equations, next, these are the equations that we've already seen, right? Good to repeat and find out. Yes. Now, this is the question that we have based on what all knowledge we have got in these few minutes. Now, vapor pressure of pure water at 100 degrees. 100 degrees is nothing but the boiling point of water. Is 760. That is nothing but 1 atmosphere, is it not? But the dilute solution of urea is 740 mm. So there is a decrease in the vapor pressure, lowering of vapor pressure. Then we have to find out the mass of urea present in 760 grams of water. Now there is a lowering of vapor pressure. The formula delta P by P naught equals XP, which you can write as WB by MB into MA by WA, which is what you have shown here. So how much is delta P from 760 to 740? The change is 20. So 20 divided by 760. The weight of the solvent is also 760. So that and this will get cancelled out, right? And then what is this WB? WB is the X that we have taken up here, right? So that will be equal to 66.66, or answer is option B. Simple usage of the formula, right? All that you need to do is identify what formula is being employed here. So there is a lowering of vapor pressure. So P naught minus P, 760 minus 740 divided by P naught is nothing but the mole fraction of the solute. Because there is a dilute solution, the denominator which was having Na plus Nb, this is Xb, is it not? We have removed this. We have ignored this because this is too small. And that is how we got this equation. Hope this is clear. Yes. We'll move on to the next question now. So during winter season in cold countries, ethylene glycol is added to water in car radiators, because what will happen when the temperatures become sub-zero, water becomes ice. When it becomes ice, it cannot flow and it cannot function as a coolant. It cannot function as a coolant. Ice is not a coolant, right? So we have to prevent the water from turning into ice. So you have to decrease the freezing point. That is what is necessary now. So for a car radiator to have water as water, right? That is a solution, aqueous solution, despite the temperatures going below 0 degrees Celsius, right? You need a substance like ethylene glycol, which can bring down the freezing point. And the freezing point is brought down to what? -3 degrees. So delta TF is 3. And that is equal to KF into M. Molality is what? WB by MB, right? Into 1000 divided by WA. How much is WA? It is 2 kg. So this 1000 is not required. I'll directly put 2 here. This molar mass of ethylene glycol is how much? 62. Ethylene glycol is what? CH2OH. CH2OH. Add up carbon 12, hydrogen 1, oxygen 16, and this will be 62, right? So that 62 we have placed here. All that we need to find out is the WB. So KF value is also given as 1.85 here. So using that, we'll be able to get the WB as equal to 201.08. I hope this is clear. Simple formula that you need to employ here, right? Sorry for putting all the worked out things on the slide, because I thought if the time is not sufficient, we may at least show this, right? And then move ahead. Now, which of the following has maximum freezing point? So this is one very important thing. Let us say that this is the freezing point of the solvent. This is freezing point of a solution 1. This is freezing point of the solution 2. Which solution will have less freezing point? More delta TF is due to more M molality. More molality, more will be the depression in the freezing point. Now you're requiring what? Maximum freezing point. So maximum freezing point means minimum delta TF. Minimum delta TF means minimum M, correct? The freezing point depression has to be less. Where it is less, look at this. How do you get the number of moles? Look at the first one. First one is urea. So 12 divided by 60, weight by molecular weight. Second one is ethyl alcohol. The molar mass is 46, CH3CH2OH. Third one is glucose, 12 by 180. Fourth one is sucrose, 12 by 342, C12H22O11. So whose M is less? 12 by 60 or 12 by 180 or 12 by 46 or 12 by 342? It is this one, 12 by 342. So this has got minimum M value. Therefore, maximum freezing point. So minimum decrease in the freezing point, therefore maximum freezing point. It is, let us look at this. Suppose you have this as the TB naught and this as the TF naught. Freezing point of solvent, boiling point of solvent. Now this is TB, boiling point of the solution. This is TF, freezing point of the solution. Now, when you have more particles, there will be more elevation of the boiling point. More particles, more depression in the freezing point. Suppose I have two solutions, TF1 and there is a TF2. There is a TB1, means solution 1, solution 2. Now this has got more elevation. So shall we say this is less M, this is more M, more M, more will be the elevation and more will be the boiling point. Here, look at this. This is less M. This is more M, and this is more freezing point. More freezing point due to less M. Because freezing point, we are going on to the other side, reverse. Freezing point is getting decreased, whereas boiling point is getting elevated. So boiling point is more for more molality, whereas freezing point is more for less molality. I want you to note this. Clear? We'll now move back to the next question now. What happens to the freezing point of benzene when a small quantity of naphthalene is added to it? Shall we say that naphthalene is a non-volatile solute? So when a non-volatile solute is added to a solvent, right, what will happen? There will be a decrease in the freezing point. So freezing point will decrease. Clear? It's a straight question, straightforward question. In the depression of freezing point, what is happening? Only solvent molecules will solidify at the freezing point. Clear? So the A and B are not relevant. They are not relevant. They are vapor pressures. We are not talking about the vapor pressure. We are talking about the freezing point. So solute molecules don't solidify. As I mentioned, most of the solute molecules are already solids, right? But what comes out is a solvent. As I mentioned, if it is an aqueous solution, what comes out is ice. So there is a solidification of the water into ice. So option D it is. Now in this, boiling point of a 2% aqueous solution of a non-volatile solute A is equal to the boiling point of a 8% aqueous solution of a non-volatile solute B. What is the relationship between their molar masses? See, when the boiling points are equal, it means that delta TBs were same. When delta TBs are same, the number of moles are same, NBs are same. When NBs are same, it means that WB by MB is the same for both the cases. Now, we'll take up the first question, first solution. 2% means what? 2 grams out of 100 grams of solution. So both are having 100 grams because this is also percentage, that is also percentage. So the grams of solution is the same. So the first one, we have 2 grams. By the molar mass Ma, that will be the number of moles of that. This is equal to 8 grams by molar mass B of the second solute. So this is the number of moles of the first solute, number of moles of the second solute. Both should be equal because their boiling points are the same. Here. So what will be MB then? MB can be write as 8 by 2 into Ma, or MB is 4 into Ma. Option B it is. I hope this is clear. MB is equal to 4 Ma. Clear? Now, this is the most important thing. When we had talked about colligative properties, we mentioned about 4 properties. We said that 3 are depending on the molality. The 4th one is dependent on the molarity. But then all were proportional to number of moles of solute. What if the number of moles of solute is not maintained? It could be that the number of moles have increased or number of moles would have got decreased. Possible? Yes. So let us look at that part. There is something called dissociation. Suppose you have an electrolyte as a solute. Electrolyte will dissociate. For example, NaCl dissociates as Na plus and Cl minus ions, right? Then you may have Al 2 SO4 taken 3 times. That will give you 2 Al3 plus 3 SO4 2 minus. So all these things will keep happening, is it not? Now, in dissociation, what is happening? Suppose you had started with an electrolyte, AB, and AB is breaking down into A plus and B minus. Let us say that alpha is the degree of dissociation, means alpha moles will dissociate out of 1 mole. So you started out with 1 mole. So initial 1 mole, 0, 0. And then final, let us say, after 1 has lost alpha, how much will remain? 1 minus alpha will remain. And let us say that these are n in number. So this will be n alpha. For example, NaCl, for NaCl, n is equal to 2. For Al2SO4 taken 3 times, n is equal to 5. So like that. So out of 1, alpha have gone and those alpha have become n alpha. So what are the total number of particles now? 1 plus alpha into n minus 1. So you thought that there was only one particle and now there are so many particles, right? So it has become abnormal. It is not the same one that you talked about. The Van't Hoff factor gave one, the scientist Van't Hoff gave one formula that any observed colligative property is I into theoretical colligative property. Observed colligative property is actually the abnormal colligative property. So this is equal to I into the normal colligative property. Normal colligative property means you have a formula. Clear? You have a formula for that. Like we wrote delta TB is equal to KB into M. Delta P by P naught is equal to XB we wrote. So like that, there is a formula. If there is no abnormality, so I is equal to 1. So I equals 1 for no abnormality. Means the number of particles are same as expected, right? But then there can be abnormality. So abnormal colligative property is I into normal colligative property. So I is equal to abnormal colligative property by normal colligative property. Or you know that abnormal colligative property will depend on the number of particles present. So 1 plus alpha into n minus 1 by 1. Normal is for the one that you started out with. But now it has become, so these are the two things that we have here. So if you solve, you'll get alpha as I minus 1 by n minus 1. This is for dissociation. Clear? Where n is what? The number of ions that come from the electrolyte. By looking at the formula, we'll be able to say that. For example, if it is BaCl2, you'll get 3 particles. If it is NaCl, you get 2 particles. So like that. So this I, Van't Hoff factor, this alpha and n are for dissociation. So this is the formula. You could also have association, but then let us take some time. So this is what we found. Clear? So this is summary that we have here. But then there can also be an association. Now it is association, what are we going to do? So let us check that part. For association, let us say that, for example, acetic acid, 2 moles of acetic acid or 2 molecules of acetic acid will join together to form a dimer when acetic acid is taken up in benzene as a solvent. So I can write here n moles of A is going to become 1 mole of AN. We could also write like this, 1 mole of A turns into 1 by n moles of AN. So that if you had started with 1 and alpha had gone, you would have alpha by n. So that the total is now what? 1 plus alpha into 1 by n minus 1. Clear? And then I is nothing but abnormal colligative property by normal colligative property. Abnormal is the number of particles that you have, observed number of particles, by what you expected. And from here you will find that alpha is I minus 1 by n minus 1. You know that alpha is always positive, right? And I is greater than 1. Therefore, 1 by n is greater than 1, right? If 1 by n, is 1 by n greater than 1? No, 1 by n is less than 1. So I has to be less than 1. So for association, I is less than 1. I'll put the dissociation formula also here. I minus 1 by n minus 1. You know that n is greater than 1. Therefore, I has to be greater than 1 because alpha is always positive. The same alpha is positive here. So if 1 by n is less than 1, I also has to be less than 1. So whenever it is association, I is less than 1. For dissociation, I is greater than 1. So small things that you have to keep a note of. Clear? So the summary of this we'll find here. So this is what we wrote here. Alpha equals I minus 1 by n minus 1. and I is less than 1 for association. Clear? So for example, here we have mentioned dimerization of acetic acid in benzene. Similarly, benzoic acid will also undergo dimerization. So how the molecules will look like? So this is benzoic acid with benzene ring and COOH. The second molecule comes up, right? Takes its OH to form a hydrogen bond like that. So you have a dimer. This is a dimer. So N is equal to 2 in this case. Trimer, N will be 3 like that. Clear? Now these are all the things that you have. You know that colligative property and molar mass are oppositely related. Therefore, observed colligative property by normal is normal molar mass by observed molar mass. Clear? Now look at this. Arrange the following solutions in their order of increasing boiling points. Now, where do you have more particles, there the boiling point will be more. So I'll do it here for you. In this itself will do. We'll use a pen that suits this. Okay. So NaCl, you know, gives 2 particles. So I'll write the number of particles as 2 into 10 power minus 4. Molarity is here given. Multiplied by the particles that you get. Here urea is NH2, CO, NH2. It doesn't dissociate. So there is only 1 particle. So 1, I'll write 1 into 10 power minus 4. So it has not got any dissociation there. Again, NaCl will undergo dissociation to give 2 particles, but then the molarity is what? 10 power minus 3. The third case, you have 2 into 10 power minus 2. So whose number of particles is more? That will be the maximum. It is an increasing order you are saying. So you have to start from less and move towards a more. So this is the least. So I'll write 2. Less than, slightly above that is 1. 1 into 10 power minus 4, less than 2 into 10 power minus 4. 2 into 10 power minus 4 is less than 2 into 10 power minus 3. So less than 3. And then 2 into 10 power minus 3 is less than 2 into 10 power minus 2. So it is 2 less than, 1 less than, 3 less than 4. Option B. I hope this is clear. Yes. Now, this is a match. Van 't Hoff factor is simply this: normal molar mass by abnormal molar mass. So A is 3. Then Kf is nothing but the cryoscopic constant. Actually, this is called the molal cryoscopic constant. Used for cryoscopy, that is low temperatures, so you can use Kf. Solutions with same osmotic pressure are isotonic solutions that we have already seen now, right? We had seen isotonic, we had seen hypertonic, we had seen hypotonic. Azeotropes, we have done this in the previous session. The solutions will have the same composition of vapor above it. Means the liquid mole fraction is equal to the vapor mole fraction. The liquid mole fraction of the other, that is others component. In fact, this is from both components volatile. So something that we did in the previous session, right? But then a question that is taken from the previous year, right, doesn't follow any rule that only these parts need to be clubbed and other parts need to be, excluded kind of. So that will not be the case. So here we have taken the question as it is. Previous year question. Now look at this. The elevation in boiling point temperature of water will be 0.1 molar NaCl and 0.1 molar urea. Urea will not break, no dissociation. That is what you have seen. But then NaCl will dissociate. So this will become 0.1 into 2 particles, and there is only 0.1 particle. So they cannot be the same. So they will be the same, cannot be true. Here. Then azeotropic mixtures boil without a change in their composition. That is what we have seen in the previous question. And then we had said that this is part of both components volatile. Osmosis always takes from hypertonic to hypotonic. Let us say that this is 0.3 molar and this is 0.2 molar. Hypotonic means less concentration. Hypertonic means more concentration. What is going to move? The solvent is going to move. Where is the solvent more? Where the solute is less. So here this is more solvent, that is less solvent. Solvent will move from what? From more side to less side. That is from hypotonic to hypertonic, not the reverse. Because what moves is not the solute, it is a solvent. Therefore, osmosis always takes place from hypotonic to hypertonic, not the reverse. Clear? And the last one here, density of, so this is also not true. This is true. The second one is true. B is true. A is not true. C is also not true. Look at the D bit. Density of 32% H2SO4 having a molarity of 4.09 molar is approximately 1.26 gram per ml. That we'll do here. It was shown there, but then we'll do it afresh because there is sufficient time. So I was having that apprehension that I might not be able to finish. That is why I had left the workings on the slide itself. Sorry for that. Right? And that is how I had to take a separate sheet and then explain on the white sheet, right, the basic working, and then take you to the summary part. All right, there is a formula here. Molarity is equal to weight percentage into density into 10 by molecular weight. Right? Molarity is what? We need to get the density. So I'll write density is equal to molarity into molecular weight by weight percentage into 10. Correct? So I'll show you this there on top because there is some space there. So molarity is 4.09 into molar mass of H2SO4 is 98. If you add up H2SO4, sulfur 32, oxygen 16, hydrogen 1. Divided by weight percentage is how much? 32% it is given here. So 32 into 10. Clear? So this is equal to how much? That we need to find out now. So how will you, is there any way that you can get the things done? Let us say that this is 100. 10 goes how many times in that? 10 times. So less than 10. So I'll write this as less than 40.9 by 32. Can we write? I have borrowed the 10 from there. 10 into 4.09 is 40.9. That less than 10 will make it less than 40.9. And then you know that 4 8s are 32. 4 10s are 40. Correct? 10s are, because it is less than 40.9. If I take it as 40, so it will be 10. 10 by 8 is what? 1.25. Approximately 1.26 is good enough. You have got it. So this is true, right? In fact, you'll get 1.26. So even without a calculation being done on a full, I mean, in an elaborate way, we have done a reasonable guess. So with this, I think I have come to an end of this session, having done the colligative properties sufficiently well, right? And seeing to it that your portion is also taken care of, right? The solutions part, which we had divided into 3 sessions, right, has been more or less completed, I shall say, successfully, taking up all the questions coming on the way, right? As we had done a concept, we had taken a question, and all these questions are from the previous year JEE main, right? Sometimes also NEET I had taken up. So we had seen to it that what all knowledge you had gained, right, you could apply and then get them solved, right, as we did, right, using formulas, right, which are all, I mean, noted ones, right? We had spent sufficient time on the derivation part also. And so with this, what all things you had required for solutions, you'll be finding in the 3 sessions. So I want you to go through the recorded videos the session 1 and the session 2 also, so that you will have a continuity there. So with this, we shall end our session. So before we conclude, let me show you the details of our YouTube channel and any other requirement that you want from time, right? Please see to it that you make the most of these sessions and then also make time your successful journey partner. So thank you. Best wishes.